lecture. Okay, outbreak investigation. Now, after we learned from our surveillance system that we do have a problem, we got updated on the various factors which we need to know about the disease, if we know, if this is a known one and not an emerging one. Still, we will not know everything. One of the things which we will certainly not know is what are the key factors driving this outbreak in our society, in our region. And therefore, we probably would prefer to find out and do an outbreak investigation. But more about this now in the lecture. Okay. Okay, reality is we hear lots about outbreaks and it catches lots of media, that's for sure. What the objectives for my lecture here is to describe steps of outbreak investigations, because if you don't already have experience, most of you in a next outbreak situation in your working environment will probably be referred to, because people will think, like, you have done a course on infectious disease epidemiology, you should be able to help us do the right things now. So I want to describe the steps of an outbreak investigation, which will probably be very helpful to follow. I will give a checklist. I want to highlight practical issues and what to look at in an outbreak investigation, and show the use of epidemiological methods. I think they are pretty useful. It's more than just counting cases. And I want to give real life examples, of course. And based on this should prepare you for this afternoon's exercise case study when you will be investigating an outbreak yourself. Okay, but first of all, what happens during an outbreak? Here in the top right-hand corner, you see an epidemic curve of an outbreak, of a epidemic on Cyprus it was. But what happens during this? In the beginning, when we see the very first cases, you see one new infected, and almost all the contacts of the newly infected individuals are probably susceptible, thus white dots, susceptible to get the infection. What happens? Of course, the epidemic progresses quickly and the numbers are increasing dramatically. So you see all the contacts got infected, and most of their contacts again are susceptible, so it can spread very, very effectively. After a while, you see the numbers are slowly declining in the epidemic curve. Why is that? Why would we expect in the very near future that also the Omicron cases are going to decrease, even though the pathogen is still very, very contagious? Yes, because now all new cases have contacts not only to susceptibles, but also to immune individuals, and therefore less people, as a consequence of one new case, can be infected afterwards. So the numbers slowly decrease. And near the end, if you wait long enough, almost all outbreaks will stop. Also, Corona will end, definitely, at least for a certain subtype for which causes the same immune response, because after a while, practically all contacts of newly infected individuals will be immune, and therefore the transmission is difficult. It will be difficult for the virus. It can either be through infection or it can be through immunization, and that's what we then would call a trend towards this often used term herd immunity over recent months. But we will come to this topic much more tomorrow. Okay, so what is the situation in an outbreak? Characteristics for an outbreak is the problem usually comes unexpected. We hear a lot about different outbreaks for different diseases, and they often come when you're not really expecting them. But nevertheless, immediate public health response may be needed. People want to have a response, and yes, if we want to have an impact, we have to be as quick, as fast as possible. The extent of the investigation might be limited because of the need for intervention. So you cannot just say, like, my power calculation tells me I need 100 more cases, so let's wait. So then the statistical analysis will be much better. No, you have to take what you get and be as efficient as possible. And you need to first, of course, as in every epidemiological investigation, to do a descriptive study in order to generate a hypothesis before an analytical study can be conducted. That's nothing new. I'm sure you are familiar with this. So the goal of outbreak investigations in general is to maximize the scientific quality of the investigation in the light of limitations and competing interests. We want to be able to give evidence or give advice based on evidence and not just on gut feelings. Okay, before we can go into the practical steps, we first have to define what is an outbreak, or first of all, what is a cluster? A cluster itself is defined as 2 or more cases related in time and or place, but may not be above expected. So if you see a number of, let's say, 5 cases of hepatitis A in the autumn in some part of Finland, you might think, oh, here are 5 cases, but this probably might be just normal, just as expected. So it would be just a cluster of cases. What is then an outbreak? If it's what is different between a cluster and an outbreak? What do you think?
I think if it now becomes unexpected, maybe 2 or more cases related in time and or place, but it's above the expected number.
Exactly. This is because cases of certain disease always occur. This is normal. But if it's more than expected, and how do you find out whether it's more than expected? I know
Surveillance, I would say.
Exactly. It's a very simple question. Sorry, I like to ask simple question, but you use your surveillance system and have a look. Oh, it's much more than expected. Okay. And how do we differentiate between an outbreak and an epidemic? What is an epidemic? Or what is different between an epidemic and an outbreak?
So I can try. An outbreak is usually outbreak is usually used for a localized excess number of cases, whereas epidemics is more widespread. The widespread outbreak, I can say, it involving a larger geographical extent beyond just being localized. But both of them are associated with an increase in the an excess in the expected number of cases for that time and that period.
Thank you very much. You've chosen your words very wisely and very carefully. You said that it's more often used for wider outbreaks, for bigger outbreaks, but in reality, but you're also right. This is the case, but an epidemic is an outbreak, and an outbreak is an epidemic. Just both terms could be used interchangeably, but in reality, then they imply something slightly different. So people are a bit more worried if they hear about an epidemic than if they hear about an outbreak. But in principle, it's in both cases, it's more cases than expected of a certain disease. So something which we would want to find out more, where we would want to find out what is the cause for this and how can we stop it. Right.
Ralph, can I ask a question, please?
Of course.
I was also thinking that epidemic, like it has also to do like with widespread, like more than one country or something.
No, more than one country. I mean, we talk a lot, or we talked a lot the last 2 years about pandemic. A pandemic is an outbreak or an epidemic which spreads beyond national borders, and normally a pandemic which crosses continents. So if it occurs in several continents, then you would talk about a pandemic. An epidemic is like an outbreak, but as everybody feels like it looks like bigger, but in principle, if you want to, if you can use both terms interchangeably.
Okay, thank you.
Oh, you're welcome. Okay, so let's look at a checklist. So if you're involved in an outbreak investigation, you have to think carefully and you have to use your time wisely. So the first step here is a list of steps and the first step would be outbreak suspected. So you get a phone call, usually, very often it is on a Friday afternoon. You just planned to, in Finland, you plan to go skiing with your friends, or in Ghana, you plan to take your family to the beach. And then there's a phone call. Sorry, this is Dr. So-and-so, but I see so many more cases this week than expected of a certain disease. You, from the health authority, you really have to do something. What is your first step? What would you do as first step in this situation? Would you first call your family or friends and say, like, have a good weekend, I'm in the office? Or would you maybe first give yourself a chance that it might not be an outbreak? Any suggestion?
You might want to find out if it's really an outbreak first before you cancel your plans.
Exactly. You first need to verify. I mean, this is one of the intrinsic motivations I just said, but there are, of course, there are also extrinsic or professional motivations. Yes, of course, you first need to verify, because not every report of an outbreak needs to be a real outbreak or a real epidemic. How can it be that one doctor reports to you more cases than expected, so many more cases than expected, and it not being an outbreak? How can this be?
Perhaps the doctor is using a wrong case definition.
Right. Do they fulfill the case definition? Absolutely. We need, again, case definition. Very good. This is one of the factors. Or lots of others. For example, a new laboratory now reports every case which before had not been reported, or. So you first verify and figure out whether it's a real outbreak, and then you probably have to start an investigation. Exactly. So is it an outbreak? More cases than expected at the same location within the same time period? And is this increase in cases real? So that's one of these are things which we really want to figure out. Okay. If this is the case, I think the next step should be to inform relevant agencies and establish cooperation. If you're the local public health doctor somewhere in whatever region in the world, then you're not the only one to deal with this outbreak. You probably want to inform, if you were in Germany, you would want to inform the state level or the national institute. In Finland, you would probably want to contact the National Institute as well, and inform those people who need to know about this, and set up an outbreak investigation team, so that you would be able to really carefully look at it and have all the expertise in your team. Yes, who would you want to have in your outbreak investigation team? Imagine, like one of the outbreaks I was investigating was in Kosovo just after the war, and I was asked to fly in and as lead epidemiologist, but with other people with a team together to investigate an outbreak. Who would you want to have in your team, in your country?
Yeah, so I would like to have Ralph Becker.
No, thank you very much. That's very kind. No, but I mean, what kind of professional colleagues would we need?
Okay, so I think it's good to have a multidisciplinary team. So
Right.
I would like to have a laboratorian. I would like to have a clinician, of course, an epidemiologist that can manage data. Very importantly, a logistician that can help sort out logistic issues. Yeah, so if it is an outbreak that involves animals, I would like to have a veterinarian as well.
Excellent.
And then some other colleagues, environmental officers may also be important to be on the team. And I mentioned a laboratory scientist as well. So basically,
I think this is a very good combination of people, because from all different aspects, and multidisciplinary is really very helpful. One person I still would add, it would be a press officer or somebody who is going to deal with the media, because of two reasons. First of all, he or she can take away all the media requests so that the team can concentrate on investigating the outbreak, and to make sure, on the other hand, that only one message is going out and not different messages of people with different knowledge. But otherwise, yes, this multidisciplinary team will really be very helpful and help you in for the following steps. Exactly. One of the next steps will now be to identify and count cases. And as Daphne kindly already told us before, is we need a good case definition, not only for a surveillance system, probably there as well, definitely as well, but now for our outbreak investigation. We need to develop a case definition with a set of conditions, mainly clinical conditions, specific time periods, because if you only talk about Q fever cases in a certain region, it would mean like all from 10 years ago. No, for a certain time period from when this outbreak started, or when you expect it to start it, concerning time and place. And the goals of case finding, as we learned this morning as well, is to identify the maximum number of cases. So thus our surveillance, our case definition needs to be very sensitive. And the second aspect should be to exclude non-cases. So our case definition should be very specific. And to do this, we learned we would probably have a different layer of case definition. Here's the WHO case definition of for the West African Ebola outbreak. And as you can see, also here they used suspected case definition. So this is very sensitive. You will have everybody potentially involved. Probable, which is most likely to be a case, or confirmed, which is definitely a case, so which is very specific. And a new patient identified can probably move from suspected via probable to be a confirmed case. So at different stages, you at least have a clear overview of the potential size of the outbreak, and you can also, for further investigation, focus on those ones who are definitely cases of the disease you're looking at. Is clear? I guess so. Daphne explained it very well, I guess. So now with our case definition, we can go out and try to characterize this outbreak. We will find cases, and we would next, as a next step, want to describe who was affected, what were the factors there, where were they affected, and when. What, who, what, where, and when. For this, we would look at time, place, and person. Okay, at these three factors. Let's first look at time. And for this, we just draw an epidemic curve. So, and epidemic curves, actually, you remember it's number of cases over time. So you have got this nice curve, which I showed you at the beginning of this lecture. And the shape of the epidemic curve will already help you to understand much more about the spread of the disease. It can be either a point source, a common source, or a person-to-person transmission, or a mix of it. But these three classical ones will help you already. The first one is a point source, and you can see typical on this outbreak is it's very short. And it rises quickly with steep rise and steep decline, quick decline afterwards. So this indicates that at one point in time, point source, at one point in time, those people who later on developed the disease were infected. This was a Christmas dinner, as you can see, just before Christmas in late December. In Rotterdam, where I used to work some years ago, and there a whole company had a Christmas party, and they had a Christmas dinner, and with traditional Dutch food, which they call Oud-Hollandse maaltijd, is very traditional Dutch dinner. But if you translate it literally, it means old Dutch dinner. Maybe it was a bit too old. And some of the components, so you saw this outbreak. Typical point source. The second option would be to see an epidemic curve which goes like this, which here over weeks, over a long period of time, increases, stays at a relatively high level for a long time, and then declines slowly. And this is what we would call a common source. Here, probably one source, an exposure over a longer period of time was available. We'll look at it in a minute in more detail. And the third option of an epidemic curve could look like this. This was the SARS epidemic, SARS-1, the SARS coronavirus number 1, 20 years ago, almost 20 years ago. And you can see a different shape. What kind of shape do we see here? Who can see a different pattern?
Propagated.
Sorry?
Propagated.
Yeah, increasing and decreasing, something like waves, isn't it?
Waves.
Waves. And this is very typical for a disease which is spread person to person. Look at for example, you can also look at the corona, COVID-19 cases reported. It also follows this pattern. Or here in this case, this outbreak from Cyprus, where viral meningitis cases are reported. You also see kind of different waves, which indicates here the disease, the pathogen, is spread from person, transmitted from person to person. Okay, how can this be? Maybe we get a bit more insight if we look also at place, time and place. Place, you probably remember, those of you who have not heard of him, this is Dr. John Snow, the founder of epidemiology. In 1855, he investigated a cholera outbreak in London, in central London, and he identified, looking at this, each line here means a case in a household was a case, and you see, looking at the geographical spread, drawing this on the map, he could see like the central point is a pump, and he identified that this pump was the source for the cholera spread there. So place is already traditionally one of the factors we like to look at. Okay, even if we combine time and place, again, our outbreak in Cyprus, you see these are big cities or larger cities on Cyprus, and these are numbers of hospitalized cases during this outbreak in Cyprus. We see that this person-to-person transmission can be explained by the virus spreading over, doing a tour of the island, starting in Limassol and then going to other places. And therefore, once most people in Limassol were affected already and thus immune, other parts of the island still were good, had a population which allowed the virus to spread. So time and place is very useful. From the same outbreak, which Mike Ryan actually originally investigated, a friend of mine from WHO, he could see the age distribution, and we can see who was affected, mainly young kids, and you can even see, and some of their parents. All right, time, place, and person. Very simple, descriptive, common sense epidemiology. This is what mainly has been done also for the corona pandemic. You always heard about the numbers of cases, maybe even the age distribution, and so on, but not much more. And I want to tell you that actually outbreak investigation, the really exciting part, the really epidemiological part, starts after that. We need to have this knowledge, and then we can look for risk factors for the spread so that we can really intervene. And for this, I would like to take you to this big city in Western Germany. It's called Dortmund, has a good famous football club, which is not doing so well at the moment. But anyway, second most important thing known from this city is that they produce good beer in a way. But they also are famous, at least in the public health arena, for this bacterium, Coxiella burnetii. We heard about this in our, just before, it's the pathogen causing Q fever. Q fever, just a reminder, appears worldwide, except New Zealand. They have managed to keep it out. The incubation period, we heard 2 to 4 weeks. And clinically, it looks like influenza with sudden fever, strong headache, joint and muscle pain, and the X-ray was an atypical pneumonia. And people can be really ill. So let's have a look at the X-ray. The medical colleagues among you probably will recognize this is a normal one. This person has good lung function. This one has a bit more difficulty to breathe because this person has Q fever, and this part of the right part, lower part of the right lung is not ventilated at all, for example, and people can be really ill. And just to tell a funny anecdote around this, one of the cases which we investigated there was from our national rowing team. And you know, the big rowing boats with 8 men rowing, which is the national team where people are really proud of, and they often win gold medals at the Olympics, or many medals at the Olympics. And one of those really strong, fit men got this Q fever during this outbreak, and he had to be hospitalized because of severe illness. And the really bad thing is, during that year, even though we usually win Olympic medals, that year, the national big boat didn't even qualify for the Olympics. So you see, infectious diseases have strong impact on the whole society. Okay, coming back to reality, to the really important things. What did we have during this outbreak? We learned about 74 cases. Most of them were serologically confirmed, more men than female, male than female, as we heard in the lecture in the presentation before. Mean age was 42 years, but with this variance between 12 and 78, so practically everybody could have been affected by this. Again, we find this epidemic curve. And now I'm wondering if you have listened to the earlier part of the presentation. What kind of sort of transmission do you expect with this epidemic curve? Was the second one I showed you before? Did anybody listen?
I'm guessing between point or common source.
It's a common source. Very good.
Common source. Okay.
Common source is so short period of time, only one short period at one point in time, the exposure. No, you're right. There seems to be it has over weeks it increases. We have high levels for a longer period of time and then slowly decreases. Yes, there must be a common source somewhere in this city. There must be something which we might find. So if you see an epidemic curve like this, you can be quite optimistic to identify. There's a good chance of identifying a common reason for this outbreak. So hey, it's worthwhile investigating. Looking at the geographical spread here, the red dots on this map indicate locations where people lived who had Q fever during this outbreak. And we can see, looking at Jon Snow, somewhere maybe here in the middle, there might be a source, or at least somewhere related to this area. Right? I hope you agree. Okay. And the age distribution, as we said, it's male, female, all age groups, more the middle age, but we don't have information whether they are not in the majority anyway in this region. Okay. So this is what we have as descriptive epidemiology. And as I told you, I think it would be sensible to move on and to investigate a bit more, to find risk factors. And for this, we need to generate hypotheses as our next step. Why do we want to, or do we need to generate hypotheses? Well, because we are humans, because that's the way we think. Referring to a philosopher, Immanuel Kant, who said, when we experience that something happens, we assume that something preceded, as it will follow a rule. So we want to, there must be a reason for it. So we want to understand the rule, the reasoning for it. At least that's the way I'm ticking. I don't know how you tick. But I think most of us do tick so if we see something like this. And I've referred to this tomorrow as well. So what would be our hypothesis? Based on the descriptive analysis and what we learned from the presentation just before is that transmission via contact to sheep feces or contact to infected sheep could play a role, would be the first two hypotheses. This neighborhood is called Assen, and we also got from the veterinarian information, serological information about the sheep in this region, which had a relatively high rate, a positivity rate of Q fever in their blood, compared to another region a little bit further away, where this rate was much lower. So maybe it has something to do with sheep. But it could also be contact to infected other animals, infected milk, especially raw milk. We learned this morning the milk should best be pasteurized. Otherwise, it can also transmit Q fever, or it could also be the consequence of tick bites. Ticks are also very common there, and they could also transmit Q fever. So, hey, what could be the factor, and can we do something about it? Let's have a look. Therefore, we need to test the hypothesis. And for this, I would highly recommend to do an epidemiological study. I hope many of you have heard about the different study designs. Cohort study and case control study are the most common ones under these circumstances. A case control study, for example, works like this. You've got cases, which are those ones we have already. We know who is ill, and we try to find controls, individuals who lived in the same neighborhood and who could have exposed to the same things and the same risk factors as the cases. And then we ask both groups, what did they do in the past? Thus, in a retrospective manner, we try to identify what the cases did and what the controls did. And if there's a clear difference, if cases did something much more often than the controls, then we assume maybe this risk factor could be causal for, at least could play a role for this outbreak, right? I hope that's so far so clear. Okay, so we did a case control study. We had 68 cases who answered the questionnaire. We sent a questionnaire out to the population there, and we got a random sample of the population and sent them also a questionnaire, and 100 of them answered. This response rate, of course, among the cases was higher than among the controls, but believe me, these numbers are exceptionally good. These days, it would be probably very difficult to get similar response rates. So we had a very high response. To compare cases and controls, you can also see that they were almost of the same age as an indicator. They are probably relatively good, well comparable. It's a good idea. Okay, so.
Maybe, may I ask a question?
Please, always ask questions.
Yeah, here maybe from our presentation this morning, most of the Q fevers, they were mild and sometimes they are asymptomatic. So when we select these controls, maybe is there any laboratory, or we just identify based on clinical manifestations?
Absolutely. This is one of the limitations. Definitely, we don't have information. We don't have laboratory tests for the control. So there could have been, some of them could have been asymptomatic Q fever cases, which we will at the end with the results have to discuss. If there are some of which we don't know, assuming that some might be asymptomatic cases, it would probably lead to the fact that our results would be diluted. So the results would not be as clear-cut as could be. So if we still see a difference, it might be even bigger. So the risk factor might be even stronger. This is a risk factor which we are, or a risk which we had to take under these circumstances. As I said in the beginning of this lecture, you have to be as scientific as possible, but under given limitations. And let's have a look if we still could find any risk factors. Okay, for this, let's have a look at some of the results. First of all, we asked whether they were on holidays, and cases and controls compared. And we see that more cases were on holidays, relatively speaking. No, more controls were on holidays, relatively speaking, than cases, leading to an odds ratio of 0.4, which means that being on holidays was a protective factor with a confidence interval less than 1, not including the 1, meaning that yes, obviously, if you can say the other way around, not being on holidays was probably a risk factor. So being in Dortmund at that time was a pretty good risk factor for developing the disease. Going to the farm in the neighborhood, could it be a risk factor? Because we saw the farm was centrally located where most of the cases were. And we see an odds ratio of 1. What does an odds ratio of 1 with this confidence interval mean? Do you think the farm was the risk factor?
No.
No, because it doesn't make any difference if you went to see the farm or not. Did it make a difference if you went horse riding to the horse riding center? Also almost nothing. There's no difference between cases and controls. Also very small numbers who did horse riding there, obviously. Okay, let's have a look at other locations. For example, if you went to Asselburg Street near the center, if you went there, not if you lived there, but if you went there during this period of time, oh wow, we see the odds ratio is 4.5. So cases were 4.5 times more likely visiting Asselburg Street than controls, with a confidence interval not including the 1, thus clearly indicating, hey, we have 1 risk factor. Being around there was a risk factor. Holland Street was a bit increased, but also not statistically significant. Okay, then let's come to the real risk factors. The strong risk factors like drinking raw milk. Do you think drinking raw milk was a risk factor?
No.
Almost nobody drank raw milk. They all follow your advice and drink pasteurized milk. Tick bites were not common, but contact to sheep manure shows a very, very high odds ratio, almost 10 times as high. So cases probably went for walks and recognized that they were among sheep manure much more often than controls. Okay, was highly clearly significant. Okay. Okay. Let's just okay, I'm a bit confused. Sorry. So how can this be? How can be sheep manure? Does any one of you have sheep at home? Not really. Okay. So typical for sheep, if you have sheep, you probably use the manure, the byproduct of the sheep in a way, to fertilize fields. And people who were there saw a much higher, saw this cases had a much stronger contact there than controls. And so we identified that being there, we investigated further and found out that actually, yes, this farm, visiting the farm, which we saw in the middle of the neighborhood, was not a risk factor, but the farm had sheep, and they delivered their lambs around this time of the year when the outbreak started. And normally if you have sheep, the manure and the placentas and whatever, all the byproducts go on a big pile, and then later on are used to fertilize fields, and they used to fertilize the fields in the neighborhood. So lots of people got infected. So we could identify this, and Based on this, the health authority put out a ban, so no more sheep lambing in this neighborhood, just outside where there are less people, and hygienic disposal of sheep products was became mandatory for this region. With this further analysis, with this outbreak analysis, and with the clear results, we could have a strong impact on public health policy, which was then also implemented. And we reported on this, for example, in information for public and professionals in the media, as you saw the newspaper, one of the newspaper articles, and we produced a written report and an article, Q fever in Dortmund during this time. So this is in a nutshell, and I'm on time. We're again on time. We've got 5 minutes for discussion. This allowed us the opportunity to really act and not wait until the next outbreak would come.